So one of the main reasons that I wanted to use these topics to close out the school year is they sort of tie together a lot of different integrating techniques and simplifying techniques that will be really beneficial to you in your Calc 3 if you've seen them before, or if you decide to redo Calc 2s to get a solid foundation, you will have seen some of these techniques that they might cover in those Calc 2s. Depending on what college you go to. So one of them is we're going to start looking at this, prove that the area of a circle is a equals pi r squared. So I have a circle here. So one of these simplifying techniques that I'm going to talk about looking for is we want to find the area of this circle. We could do, as most people did, by the way, for their mini project, they did integral from -r to r, and then they did that volume of rotation, okay? But we know that the two sides of this are symmetrical. So an important simplifying technique to look for is look for a simplifying symmetry. And then, instead of doing my integral from -r to r, I can go from 0 to r, and very often using that 0 is going to simplify one end of the limit evaluation, and so it's very profitable to do a lot of the time. And the other thing I'm going to do is not worry about the part below. So technically, if I conceive this area in terms of an integral, it will be the integral from -r to r of the top function minus the bottom function. So it would be square root r squared minus x squared minus negative square root r squared minus x squared, which is the bottom half of the circle. All right, but we're not going to do that. Instead, we'll say we will find it sufficient to find the area of one quadrant of the circle, and then just multiply that by 4. So what we can start by saying is that the area of the circle is equal to 4 times the integral from 0 to 4 of the square root of r squared minus x squared dx. All right, so now what you come up against is you really have no way to integrate this. You can look at a lot of different techniques. The reason I had you guys do the sphere on your own is because the rotation volume formula has you square the integrand. So you square the function that you're doing, so the square and the square root cancel out. So most people saw that. Or some people did a great simplification where they just never solved for y in the first place, just left it y squared equals r squared minus x squared, so plug that right in. In the circle, the two-dimensional circle, we don't have that luxury. The square root does not cancel out. So we have no immediate way to do this integral. You can think about things like u substitution. If I did u substitution, my u would be r squared minus x squared. My du would be negative 2x dx. I don't have a negative 2x dx out here. So I can't do that. None of our parts doesn't work. None of the techniques that we've learned so far works. And nothing that you've learned yet will do this integral. All right, so that's what we're going to learn. It's a technique that handles these kind of square root expressions, radical expressions. So the first one that we're going to learn, actually the only one we're going to learn since the end of the year, is called trigonometric substitution. And so this is a very clever idea for handling integrals like this. So in trigonometric substitution, it's like a u substitution, but we're not substituting for something that's already there. What we're going to do is we're going to substitute in something else that will simplify the problem somehow. So what we do is we say, let x equal r sine of t. So r, remember, is just a constant. So if you had 4 here, we'd put 2 sine of t, because this is r squared. All right, so r is just a constant. So we're really inventing the variable t. And we're going to substitute that in for the x squared here. And then we do the same things that you usually do for a u substitution. So we're going to say what the dx is. Now remembering that r is a constant, that dx is going to be r cosine t dt. All right. Now that sets up a different integral in here, but before we get to that, normally when I do a u substitution, I don't change the variables up here. By the way, you see that 4 right there? That's actually supposed to be an r. That's supposed to be integral 0 to r, right? Integral 0 to r. All right. So normally when I do a u substitution, I just leave the limits. Remember, that's just sort of a shortcut that I've taken a lot that is kind of sloppy, but it works, and I like it. In this particular integral, it makes it a lot harder if you don't change the limits of integration. And so it's also, among the techniques that we look at, it's really good to look at that sometimes it's really advantageous that when you change the variable, you also change the limits of integration. There are some professors who will say you cannot do a u sub without changing the variables, and they're not wrong. but you can sort of invent a shorthand to get around it. So here's what we're going to do, though. We're going to change these variables because these variables, these limits up here pertain to x, and we're going to change this variable to be in terms of t. We're going to change the integrand to be in terms of t. There's going to be no x left in here. There's only going to be t's. So that means that these limits of integration need to change to values of t. So what we're going to do is look at what happens when x equals 0, what happens when x equals r. So when x equals 0, then your x equals r sine t becomes 0 equals r sine t. And it's not too hard to figure out from that if we want x to be 0 and our t is going to be between 0 and 2 pi because it's on this circle. So that means that t has to be 0 because sine of 0 is 0. All right, and then when x equals r, what's going on? Then when x equals r, we have r equals r sine t. All right, that's just substituting the r for right there. So that tells you that 1 equals sine of t, and we know that sine of t is equal to 1 when t is equal to pi over 2. All right, so now with this substitution of limits and this substitution for the integrand, we can now say that the area of the circle is equal to 4 times, that's keeping the 4. We're going to do the integral from, our 0 to r becomes 0 to pi over 2. 0 to pi over 2. So interestingly, the r sort of disappears from the limits. And then for my square root, I'm going to have r squared, and then I'm going to have minus, this is x squared, and x equals r sine t. So when I sub the r sine t into the x squared, I'm going to get r squared sine squared t. Then my dx is going to become r cosine t dt times r cosine t dt. All right, so that's what we've got there, and then we're going to proceed to evaluate that in the next video.